Hello everyone, welcome to this 18th lecture in the NPTEL course on Riemannian geometry. So in the previous lecture we've been talking in the past few lectures about connections, about covariant derivatives of vector fields and so on, and then in the previous lecture I introduced a very sort of special connection that exists on Riemannian manifolds called the Levi-Civita connection. It satisfies two properties. It's a metric connection and it satisfies a certain symmetry property which we call torsion freeness. So in today's lecture I would like to discuss some additional properties of connections and maybe tie up some loose ends before we can move on to curvature, which is the topic for the next few lectures. Okay, so the first thing I want to talk about is how to extend the notion of covariant derivatives to tensors, to arbitrary tensors, not just vector fields. Okay, so the first step in doing this is to talk about the right. So the first step is to talk about the covariant derivative of one forms. Okay, so so the main question we would like to address is the following. Given, let's say, a one form alpha and let's say a vector field here, what does taking the derivative of alpha with respect to x mean? Okay. So I mean, more generally one would like to so more sort of abstractly one would like to construct like a map which I continue to denote by nabla. So that takes in a vector field, it takes in a one form and spits out another one form, right. So symbolically it takes in x alpha and spits out the derivative of alpha with respect to x. So we want that derivative of alpha with respect to x to be another one form. Okay. So in other words, one can reformulate the question. I mean, what is a one form after all? That's just a C infinity linear map on the space of all vector fields, right. So one can reformulate this question to ask for the following. So given x and y, two vector fields, and given a one form, what is the derivative of alpha with respect to x acting on this vector field y, right. So if whatever rule we come up with, if that happens to be also C infinity linear in y, then we are basically done, right. Then that would answer the original question. Okay, so the key point in order to guess at the right formula is to impose a certain Leibniz rule. So what do I mean by that? So let's say I take alpha acting on y, that's a smooth function, so I can differentiate it with respect to x. Well, I want the following Leibniz. I mean, if Leibniz rule were to be true, then when you applied x to alpha alpha acting on y, that would be the derivative of alpha with respect to x. So that is what I am denoting by this acting on y, plus alpha acting on the derivative of y with respect to x, right. So any reasonable Leibniz rule would look like this. But now I can just turn this around and use this to actually define this quantity. This is the quantity I am interested in. On the other hand, these two are quantities that I know we are familiar with. So one can just use this formula to make a definition for the covariant derivative of alpha. So here's a definition. So given x, y in the space of vector fields and given a one form, we simply define nabla x alpha acting on y to be given by x acting on alpha acting on y minus alpha acting on this. Okay, so my claim is that this is C infinity linear in y. So the claim is that if you compute this, you will end up with this. Okay, so this is a nice exercise. I'll leave it to you to check. Okay, but as a result of this, so this implies that I can now think of alpha x, nabla x of alpha to be a one form. Okay, so this completely answers the question that we posed. So of course, in order to do calculations, one needs a local expression. So locally, let's see what this looks like. So let's say I have a frame. So let E be a let E be from E1 to En be a frame, be a local frame for the tangent bundle on some neighborhood U, and let epsilon 1 up to epsilon n be the dual basis. Okay, and suppose gamma I, j, k are the Christoffel symbols. Okay, so let me remind you what that means. That just means that if you differentiate Ej in the direction of Ei, you basically get gamma ijk times Ek. Okay, so now my claim is that if you take the dual basis epsilon, a dual basis element epsilon k, and now differentiate it with respect to Ei in this new sense that I have just defined, then that is going to be just minus gamma ijk times epsilon j. Okay, so let's prove this. So each side is basically a local one form, right? So if you look at the RHS, let's say applied on some basis vector EL, that's just going to be minus gamma ijk epsilon j applied to EL, but because epsilons are the dual basis, this is going to be minus ijk delta jl. Okay, so now if you sum over all possible j's, because that's the repeated index, the only non-zero contribution is going to be when j is equal to L. So this is going to be minus gamma ILK. Okay, so that's the RHS applied to a basis vector EL. Now what is the LHS applied to a basis vector? So LHS applied to a basis vector EL, so that is the derivative of epsilon k in the direction of EI applied to EL, but by my definition that's just EI applied to epsilon k applied to EL, right? minus epsilon k applied to the derivative of EL with respect to EI. That's just the definition that I have made, right, of covariant derivatives of forms. Now, if you notice that this thing, this is going to be delta KL, right? So it's either always 0 or always 1 depending on the indices KL, right? In other words, it's a constant function, no matter whether if k is not equal to L, it's constant 0, if k is equal to L, it's constant 1. So when you differentiate, that's going to give you 0. So this entire term is going to give you 0. So this is going to be minus epsilon k, and then by the definition of Christoffel symbols, this is just this. Okay. So by the C infinity linearity of one forms, this is simply this, which is minus gamma ILJ delta Kj. Okay. But now again you are summing over the repeated index, which is j. So the only non-zero contribution is going to be when j is equal to k. So this is going to be minus gamma ILK, which, if you remember, was the same thing as the LHS applied to EL. So for any basis vector, the RHS applied to the basis. So for any vector EL, the LHS applied to EL is the same as the RHS applied to EL. This implies that as one forms, the LHS is equal to the RHS, and we are done. Okay. All right. So sort of more generally, one can use this formula to calculate what the covariant derivative should look like on forms. So if alpha is given by let's say locally as alpha k epsilon k, then the covariant derivative in the direction of EI of alpha is this. Now you can check from the definition, I mean we already right, so you can check from the definition that the covariant derivatives of one forms also satisfies all the defining properties of the covariant derivatives of vector fields. In particular, this means that in this entry it is C infinity linear, it satisfies Leibniz rule. Okay, in particular that means that this is simply EI acting on alpha k times epsilon k plus alpha k times the covariant derivative of epsilon k in the direction with respect to EI, which is just this times epsilon k plus alpha k times whatever our claim is, which is minus alpha k gamma I L k epsilon L. Okay, so in other words, I can sort of combine terms and write this as the following. So I'm just changing sort of the indices around. Okay. So this quantity here I denote by this. So this is the jth component of this covariant derivative. Okay. All right. So so a special case is of course when you have local coordinates. So x1 up to xn are local coordinates, and then you can take E1 up to En to be the standard basis del 1 up to del n, and of course then the dual basis will look like dx1 up to dxn. So then we have the following, that if you take the covariant derivative of alpha in the ith standard direction, then the jth component of that is simply given by del alpha j by del xi, and then some correction term coming from the connection. Okay, so then this is simply this. Okay, so that gives you local formula to calculate what the covariant derivative will look like. So now the next thing I want to do is to try to extend this to general tensors. So we have now, of course, by definition we have the covariant derivative of vector fields. Now in the first part of today's lecture we have introduced covariant derivatives of forms. So now we would like to do this for general tensors. Okay. So again I'll pose a similar question. So let's say I am given a vector field x, and let's say I am given a tensor of type AB. Okay. Then what is the covariant derivative of t in the with respect to x, and I want that to be another tensor of the type AB. Okay. So what is the appropriate definition? So recall that tensors of type AB are basically C infinity multilinear maps on this product, right? So A copies of one forms and B copies of vector fields. Okay. So so again, suppose now you are given omega 1 to sorry, maybe I think I had right. So suppose you are given A1 forms and you are given B vector fields, right? Then again, in order to guess a definition for this, the action on all of these, I again go back to a sort of Leibniz rule. I want to have some sort of a Leibniz rule. So what I do is the following: I apply t to these guys. Okay, so that's going to be a function, so I can differentiate it with respect to x. And then again, if I want to impose some sort of Leibniz, the answer better be this. Plus t applied to the derivative of omega 1 with respect to x, comma omega 2 up to omega a, x1 up to xb, all the way, so dot dot dot, all the way up to the covariant derivative of omega a, and then of course you also have to differentiate the vector field parts. dot 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 etc. until the final term, which would be something like this. Okay. So this is the most natural Leibniz rule, but then again, as we did with one forms, one can turn it around to actually define this quantity. Okay. So I'm not going to again rewrite this humongous expression and simply write that one can take this as the definition of this, and then again one has to check. It's a more tedious form of the earlier exercise that I wrote, that this again gives you an AB tensor. So what do you have to check? You have to check that it's C infinity M multilinear. Okay. So it's just a more tedious form of the exercise that I wrote up earlier. Okay. All right. So maybe it's nice to observe the following. So let's calculate out an example. Let's take the Riemannian metric itself. So recall that a Riemannian metric, so if G is a Riemannian metric, then G is a tensor of the type 0, 2. Okay. So let's calculate what happens when you take the covariant derivative of G with respect to Z. So this will again be a 0, 2 tensor, so it will act on x, y, which is what, by our definition, this is simply Z acting on G of x, y minus G of the derivative of x with respect to Z comma y minus G of x comma the derivative of y with respect to Z. Okay. But now you notice the expression on the right is quite familiar, right? So if G is a metric connection or is a metric compatible connection, so in particular if it's a Levi-Civita connection, then the right hand side is identically 0 for all x, y, z. So that means, being a metric connection, is actually equivalent to the following statement, that the covariant derivative of G with respect to Z is 0 for all Z. Okay, so now we have a much nicer way of writing what it means for a connection to be a metric connection, namely its covariant constant, in the sense that the covariant derivative with respect to any Z, any vector field Z, is identically 0, right? Okay, so additionally one can also try to write down a formula, so that's much more sort of complicated looking, but I think just for sort of completion's sake, let me write down the formula. It's quite complicated looking, but nevertheless I think you should maybe see it at least once. Okay, so if you differentiate a tensor in the direction of delta m, so I am taking coordinates x1 to xm, then the I1, IA, J1, JB component of this tensor will look like the following. So of course the first term, up to 0th order approximation, the first term is the ordinary derivative of this component, but then there will be correction terms coming from the Christoffel symbols. So you'll have the connection terms will look like the following. So S from 1 to A, where A is the order is the contravariant order of the tensor. IS TI1 up to IS minus 1, but IS you have already pulled out, so instead of that you have an IS plus 1 up to IA, and then the covariant parts of the tensor you keep untouched. But then you also have a connection term, a correction term coming from the covariant parts of the tensor. So that's S going from 1 to B, gamma M JS J TI1. So now you keep the contravariant parts untouched. J1 up to JS minus 1, JS plus 1 up to JB. So in both these cases you have this index I here, this index I here. So by Einstein summation you are also summing up over all possibilities for I. Similarly here you have this repeated index which you are again summing over. Okay, so that's the sort of complicated local expression of the covariant derivative of a tensor. Alright, so the final thing I want to say about connections is basically a useful computational tool. So when we are doing calculations, this next proposition will be extremely useful. This is basically the existence of what are called as normal coordinates. This will make a lot of our calculations much simpler. So here's the proposition. For any point P, there exists coordinates centered at P. So that just means that all the xi's are 0 at P, such that the following happens. If you look at the corresponding metric components Gij, then and look at its Taylor expansion will look like this. There's some constant term which in this case will just be delta Ij, which is the Euclidean metric in these coordinates, plus generally in Taylor expansion you also have a linear term, but the point is that you can make educated choice of coordinates or a clever choice of coordinates so that the linear term disappears and you're only left with a quadratic term and all the higher order terms, right? So that is denoted by O of mod x squared. So i.e. that means that your Gij at the point P is delta Ij, because P, remember, corresponds to 0 in these coordinates, and delta Gij, the derivative with respect to any xk is 0 for all ijk. Okay. So in particular what this also means, if you go back to our formula for the Levi-Civita connection, sorry, I should right. In particular, if this is the Levi-Civita connection with Christoffel symbols gamma ijk, then at P gamma ijk would all be 0. Okay. So as a consequence of this, so maybe I should say that here's a definition. Such coordinates are called normal coordinates at P. Okay. So the proof is actually by these things called by using geodesics and exponential map. So this is these are notions that we are going to introduce a few lectures down the line, and I promise this is the first and the last time I am going to state a result which I am not going to prove immediately, which I am going to prove in the future. There is actually a proof that avoids geodesics and exponential maps. There is an elementary proof by just essentially what you do is you make some arbitrary choice of coordinates. By Gram-Schmidt process, you can ensure that at P Gij are basically delta Ij, but then with respect to that those coordinates, the Taylor expansion will also have a linear term, and then there is a clever choice of sort of quadratic change of coordinates that you can make to kill the linear term. So there is an elementary way of proving this, but in the interest of time I am not going to elaborate on that. As I said, we will give a much more geometric proof of this this proposition, maybe I think 8 to 10 lectures down the line. However, maybe I'll close this lecture by making the following remarks. Firstly, this holds only at P, only at the center of the coordinate system. Okay. So for instance, if Q is not equal to P, then this may not be 0. Or this may not be delta Ij. Okay. The second point is that no matter how clever you are, one cannot actually get rid of the O of mod x square term, so the quadratic terms, by a clever change of coordinates. Since the quadratic term actually encodes information about the curvature. So the philosophical point here is that the reason why you are able to make the Christoffel symbols vanish at a point is because the connection is not really a tensor. So right, because in this entry this is not equal to f times the connection applied to y, right. So it's not C infinity linear, so it's not really a tensor. On the other hand, curvature, which we'll define in the next lecture, happens to be a tensor, and so then by a clever choice of coordinates you can't just make it 0, right. So because it's a tensor, it sort of depends intrinsically on the geometry of the manifold you're looking at. Okay, so that's one point. That's one important point. The third point is, how is this computationally helpful to us? Because then at P, if you take any tensor, apply the covariant derivative, then that's just going to be the ordinary derivative. But again, the key is only at this point P, not at any other point, only at the center of my normal coordinate system. Okay. But even so, this as we will see in the next couple of lectures, it will actually help us with our calculations a lot of the times. Okay. All right, maybe I will stop here. So that essentially finishes our discussion of connections. From next time I will introduce curvature. So for that, from now on, throughout the entire course, whenever I talk about a connection, I will always mean the Levi-Civita connection. Now we are not going to worry about other connections on the manifold, we are only going to talk about the Levi-Civita connection. So given a Levi-Civita connection, we will talk about its curvature for the next few lectures, and after that, that will sort of end the first part of the course. After that, we will then move on to talking about the metric aspects of Riemannian manifolds, namely geodesics, distances, and so on. Okay, so so that's it for this lecture. Thanks for your attention, and I'll see you in the next lecture. Thank you.